This question is from GATE 2018 paper, and this question belongs to operating system. So coming to the question statement, consider a system with 3 processes that share 4 instances of the same resource type. Each process can request a maximum of k instances. So the resource instances can be requested and released only one at a time. The largest value of k that will always avoid the deadlock is. So this is what the question statement. Okay. So according to the question statement, let's consider the data. So it is mentioned that 3 processes are there. So number of processes is equals to 3. And they are sharing total 4 number of resources. So 4 instances of the same resource type. So means that the number of resources is equals to 4. Okay. So each process can request a maximum of k instances. So means that each process demand is k. The resource instances can be requested and released only one at a time. The largest value of k that will always avoid the deadlock is. So with respect to the deadlock, to avoid the deadlock, okay, so with respect to the deadlock concept, in a system, if I want to avoid the deadlock, we have a condition. So what is that condition is, to avoid a deadlock, what is the condition is, demand of all the processes is less than the number of processes plus number of resources. So demand of all processes, what is the how many processes I have? 3, and each one is having a maximum of k instances of demand. So means that 3 into k. So this is what the total demand of all processes. So 3 into k is less than number of processes is 3 plus number of resources is 4. So 3k is less than 7. So then k is less than 7 by 3, which is 2.333. So like this. So k value must be less than 2.33. So as it is saying that, so k value must be less than 2.33 means that the close value which is less than this 2.33 is k is equals to 2. So for 2, this condition is going to get satisfied. So means that if the demand of each process is 2, then we can have, there is no deadlock. Then we can say there is no deadlock. So that's why the largest value, so less than 2.33, so k is less than 2.33. So 2.33 less than means I can have less than 2.33, I have 2, 1. Among these values, which one is the largest one? K. Which is the largest one of the k? That is 2. So that's why k value is 2. So for k value is 2, this system is not facing the deadlock. Okay. So that's why the answer for this question is 2. Thank you. This question is from GATE 2018 question paper, and this question belongs to operating system. So coming to the question statement, consider a process executing on an operating system that uses demand paging. The average time for a memory access in the system is m units if the corresponding memory page is available in memory, and d units if the memory access causes a page fault. It has been experimentally measured that the average time taken for a memory access in the process is x units. Which one of the following is the correct expression for the page fault rate experienced by the processes? Option A, d minus m by x minus m. Option B, x minus m by d minus m. Option C, d minus x by d minus m. Option D, x minus m by d minus x. So this belongs to demand paging. Okay, so demand paging. This question belongs to demand paging. So according to the demand paging, The performance of demand paging is calculated like this. So performance of demand paging is calculated like this. So if M is the memory access time and S is the page fault service time and P is the page fault rate, then effective memory access time or effective access time is equals to P into S plus 1 minus P into M. So this is what the formula which we are going to use this particular question. Okay. So here page fault. So what is the meaning of page fault is if the requested page of the CPU is currently available in the main memory, then it is said to be page hit. If it is not available in the main memory, then it is called page fault. So when that page fault is occurred, then we need to service that page fault. So what is the meaning of servicing is bringing that particular page from secondary memory to main memory. For that it takes some time, which is called page fault service time. So that is what the meaning of page fault service time. Okay. So these are what the parameters here, right? So according to the question statement, what is M, what is P, what is S? So these things we need to gather now. So according to the question statement, it is mentioned that the average time for a memory access is in the system M units. So means that M is given as M only. The memory access time is given as M. And if the corresponding page is available in the main memory. And D units if the memory access caused page fault. So means that page fault service time is given as D. And we need to calculate page fault rate. And effective memory access time, it is given that X units. So this value is given. This is given as X and we need to calculate P. So that means that, so X is equals to P into S. What is the P into S? P into D. Okay, P into D plus 1 minus P into M. Then it is X equals to PD into M minus MP. Then this I can write as X minus M is equals to PD minus MP. PD minus MP. Then this I can write as X minus M is equals to P into D minus M. So we need to calculate page fault rate so that this expression I can write as P is equals to X minus M by D minus M. So X minus M minus D minus M, which is matching with option B. So option B is the answer for this question. Okay. Thank you. This question is belongs to this question is from GATE 2018 paper and this question belongs to operating system. So coming to the question statement here, consider the following solution to the producer-consumer synchronization problem. The shared buffer size is N. 3 semaphores empty, full and mutex are defined with respect to initial values of 0, N and 1. Semaphore empty denotes the number of available slots in the buffer for the consumer to read from. Semaphore full denotes the number of available slots in the buffer for the producer to write to. The place holder variables denoted by P, Q, R and S in the code below can be assigned either empty or full. The valid semaphores are wait and signal. Okay, the valid semaphore operations are wait and signal. Which one of the following assignments to P, Q, R and S will yield the correct solution? So option A, it is mentioned P full, Q full, R empty, S empty. Option B, it is mentioned P full, P empty, Q empty, R full and S full. Option C, it is mentioned P full, Q empty, R empty, S full. And option D, it is mentioned P empty, Q full, R full, S empty. So this is what the question based on producer consumer problem. So of course the main point here is semaphores. Okay, so using semaphores we can easily solve this particular producer consumer problem. So producer consumer problem. producer-consumer problem. So coming to the producer-consumer problem, what is the statement of the producer-consumer problem is, producer process, what is the functionality of the producer process is, producer always produces items into the buffer and consumer always consumes the items from the buffer. But the condition with respect to this producer-consumer problem is, this is what concentrated point, that is, producer is not allowed to produce the items into the buffer when the buffer is full, and consumer is not allowed to consume the items when the buffer is empty. So the producer is not allowed to produce items when the buffer is full, and the consumer is not allowed to consume the items from the empty buffer. So by having this idea in mind, which values we need to assign to the PQRS in the given producer process and consumer process? That is what the question. Okay. So what is the producer process it has given? So for the producer process, the code is given that weight of P, add item to the buffer, signal of mutex, weight of P, weight of mutex. So here I can write as weight of mutex. Before that I have weight of P. Right. So now add item to the buffer and then signal of mutex and signal of Q. So this is what producer process. Next, coming to the consumer process. So consumer process, weight of R, weight of mutex and consume item from buffer, signal of mutex and signal of yes. So this is what producer and consumer processes as per the given question. Okay, and here it is mentioned that shared buffer size is n and 3 semaphores empty, full and mutex are defined with respect to initial values of 0, n and 1. So the initial values of empty, full and mutex. So here for empty it is given 0, for full it is given n and mutex value it is given as 1. Okay, these are the initial values. And have a concentrate here. Semaphore empty denotes the number of available slots in the buffer for the consumer to read from. Okay, so semaphore empty denotes the number of available slots in the buffer for the consumer to read from. Semaphore full denotes the number of available slots in the buffer for producer to write. Right. So here, what is option A? P full, Q full, R empty and S empty. So option A, if I consider P, Q, R, S, P full, Q full, R empty, S empty. So means that here it is, I can say full, here also I can say full, and here I can say empty, and here also we can say empty. Right. So let's execute with these operations. I mean with these values of P, Q, R, S, we can start execute the producer and consumer process. What happens? Have a check. So first producer, weight of full. What is the full value? N. So which can be successful, then I can come to the weight of mutex. What is the mutex value? 1. So which can be successful, so that I can add an item to the buffer. Then signal of mutex, which is mutex becomes 1 now. So now this is n minus 1. So previously this is n. After weight operation it becomes n minus 1. Then weight of mutex. Mutex value is 1. Then after weight operation mutex value becomes 0. Then by making full is n minus 1 and mutex is 0, this producer process of produced that item into the buffer. Then signal of mutex. So signal of mutex is previously it is 0, now it becomes 1, and full. Signal of full. What is the signal of full? Full is now n minus 1. Now signal of full means it becomes n. So means that producer process is successfully executed. Then coming to the consumer process. So weight of empty. What is the empty? 0. So if weight of empty, if I execute, this consumer is going to, so empty is 0. So on which you are going to implement weight operation, it means that this consumer process is going to struck in this first instruction only. So in the first instruction only he is going to struck. So it means that this producer can keep on produce the items, but this consumer process never consume an item from the buffer. So with option A, producer can keep on produces the items, but consumer never consume any item. So that's why option A is not answer for this question. So producer has to produce the items and consumer also should consume the items. But according to the option A, it is allowing, option A is allowing only producer to produce the items into the buffer. But it is not allowing the consumer to consume any item. So hence option A is not correct for this question. Now coming to option B. So what is option B is, coming to option B is, it is saying that PQ empty empty and RS is full full, right? So now this is empty, P and Q, P and Q. So this is Q, so here this is empty. Okay, so and RS, R and S are the consumer statements. So R is full and S is also full. So if it is the case, then what happens? Have a look. So first if I start executing this producer process, what is the empty value? Initial value for empty is 0. So this producer is trying to perform weight operation on this empty semaphore whose initial value is 0, which can be successful. Means that producer is strucking in the first instruction. Then if I go to the, so since he is strucking in the first instruction, he can't produce any item. But coming to consumer process, weight of full. What is the full? N. So means that initial value of the full is n, after weight operation it becomes n minus 1. So means that the first instruction is executed. And coming to second one. So what is the second one? After first instruction is executed, then consumer is coming to the second instruction. So this consumer is executing in the second instruction is weight of mutex. What is the mutex value? 1, which can be successful. So previously it is 1 before weight operation, after weight operation it becomes 0. Then he is consuming. Yes or no? He is consuming an item here. But this producer have not produced any item. He is tracking in the first instruction only. Without producing an item into the buffer by the producer, how a consumer can consume an item from the buffer? According to the producer consumer problem statement, producer is not allowed to produce items into the buffer when the buffer is empty, when the buffer is full, and consumer is not allowed to consume an item from the buffer when the buffer is empty. The consumer is not allowed to consume an item from a buffer which is empty. But here the buffer is empty, na? So he is not yet produced. The producer have not yet started producing an item. But the consumer is able to consume the items, which is wrongly construction. So we are allowing the consumer to consume the items from the buffer even though the buffer is empty, which is wrong. According to the producer consumer problem statement, consumer is not allowed to consume an item from the buffer when the buffer is empty. But according to this code, the consumer is able to consume an item from the buffer when the buffer is empty. So hence, option B is violating the producer consumer problem statement. So hence, option B is also not answer for this question. Next, coming to option C. So option C, it is saying that P full and Q empty, R empty and S full. So full, empty, empty, full. So means that here weight is full, weight of full and signal of empty. Right. So coming to consumer, R and S, empty and full. So weight of empty and here signal of full. So these are the statements now. Right. So let's execute this particular code now. So weight of full. Now producer process we started execution. Weight of full. What is the full? N. So full is N, and when I perform weight operation on this becomes N minus 1. So means that the first instruction with respect to the producer process is successful. Then come to the second instruction. Weight of mutex. What is the weight of mutex? Mutex value is 1 before performing weight operation by the producer. After performing the weight operation on the mutex by the producer, the mutex value becomes 0. So these two are successful. Then this producer is able to add an item to the buffer. After that, what the producer is doing, he is signaling the mutex. So mutex value is 0. After signal, mutex value becomes 1. Then signal of empty. What is the empty? 0. After performing the signal, it becomes 1. So it means that one item is filled. One item is filled in the buffer. So here full means the number of available slots in the buffer for the producer to write, and empty defines the number of empty slots, the number of available slots in the buffer for consumer to read. So now empty is becoming 1. So it means that one location as part of the empty buffer, as part of the buffer, one location is available to read, to consume. Yes or no? So this is what producer functionality. Now coming to the consumer. So now till now the producer have produced one item here. Now consumer. So what is the empty value? 1. At the end the consumer value, the producer made that empty is 1. So it is 1. After performing weight operation it becomes 0. Then mutex value is 1. After performing weight operation on this mutex, then it is going to become 0. Then consumer item. Then signal of mutex. Mutex value is 0. After performing the signal operation it becomes 1. Signal of full. Full is how much? N minus 1. Then you are incrementing that. So signal operation means that the signal, the full becomes again N. So means that one item is produced by the producer, one item is consumed by the consumer. Now full is N. So what is the meaning of full is N? So full denotes the number of available slots in the buffer to read, to perform write operation by the producer. Okay. So one item is produced, one item is consumed. For example, now we are saying that the buffer is empty. Now we are saying that the buffer is empty because it is making empty, empty is 0 again. So with this empty, if I start again execute, after one item is consumed by the consumer, immediately if I start executing the consumer, then what happens? He is going to stuck here because empty is 0 now. So since he is 0, this consumer is going to stuck in the first instruction. Then if I take the preemption towards the producer, then this producer, now at the end the consumer have made the full is N. So then it becomes N minus 1. Okay. So then the mutex value is previously it is 1. Now it becomes 0. Then this producer can produce an item. After producing an item, then signal of mutex. What is the mutex value? 0. Then it is becoming 1. And signal of empty. It is previously 0. Now it becomes 1. So after producing one item, then this empty becomes 1, then it can be successful. And anyway this mutex is 1 and this is also can be successful, then consumer is able to consume an item. So this way one item is produced by the consumer and one item is produced by consumed by the consumer. And this consumer is unable to consume an item when the buffer is empty. And this producer also unable to produce an item when the buffer is full. Okay. So hence the answer for this question is option C. So option C is giving the correct implementation. Producer is unable to produce an items into the buffer when the buffer is empty, when the buffer is full, and consumer is unable to consume an item when the buffer is empty. So it is correctly operated with this option C. So hence we can say option C is the answer for this question. And if you check with the option D, it is also not the correct implementation for this producer and consumer problem. So the final answer for this question is option C. Okay, thank you. This question is from GATE 2018 paper. Okay, and this question belongs to operating system. So coming to the question statement, consider a storage disk with 4 platters numbered as 0, 1, 2 and 3, 200 cylinders numbered as 0, 1 and so on 199, and 256 sectors per track that is numbered as 0, 1, 2 and so on 255. The following 6 disk requests of the form, so the disk request structure is given like sector number first, and then cylinder number and then platter number are received by the disk controller at the same time. Okay. Next, currently the head is positioned at the sector number 100 of cylinder 80 and it is moving towards higher cylinder numbers. The average power dissipation in moving the head over 100 cylinders is 20 milliwatts. For reversing the direction of the head movement once is 15 milliwatts. Power dissipation associated with rotational latency and switching of head between different platters is negligible. The total power consumption in milliwatts to satisfy all of the above disk requests using shortest seek time first scheduling algorithm is dash. Okay, so coming to the question statement, here it is given that the disk request, the disk request structure is given. So what is the disk request structure? So first one it is sector number, next one it is cylinder number, and the next one it is platter number. Okay, so here currently the head is positioned at sector number of 100 of cylinder 80. Okay, so means that we need to consider mainly cylinders. So among all the disk requests, so the disk requests are, the first one is 120, 72, 2. And the second disk request is 180, 134, 1, and the third one is 60, 20, 0, and the fourth one is 212, 86 and 3, and the next one is 56, 116, 2, and the last one is 118, 16 and 1. Okay, so these are the disk requests we have. So among them, so cylinder number is the middle one, so that the remaining, only the middle ones we are going to consider here. So what are the middle ones here? So 72, 134, 20, 86, 116 and 16. Fine. So, and it is mentioned that 200 cylinders are there, that is 0 to 199. So let's suppose 0 to 199 we have cylinders here, and it is clearly mentioned that the currently head position is at 80. So after 0, what is the next one we can come? 16. Then after 16 we can have 20. Then after 20 we can have 72. After 70 we can have 80. Then 86. After 86 we can expect 116 and then 134. And currently the disk head is here. So since it is shortest seek time first, from this which one is the closer? So if you consider 80 to 72, it is the distance of 8. If you consider 80 to 86, it is a distance of 6. So which is a shorter one, so that head moves to 86 now. Then from 86 to 72. From 86 to 72 if you consider 86 to 72. It is 14. Yes or no? 86 to 14. But here this side it is 30. So since it is shorter one, the disk head takes a reverse direction or change in the direction movement, that is towards the 72. Now from 72 if you calculate the distance to 20, it is 52. From 72 if you calculate the distance towards the 116, it is 44. So here it is 52 but it is 44. So that from 72 we travel to 16, 116. which is 44 is the distance, and here it is 86 to this is 14, right. So now from 116 we go to 134, which is 18 is the distance. Then we can come to 20. Then we can come to 20. So 134, 20, which is 114. Then we go to 16th cylinder, which is 4. So therefore, total head moments is equals to so 14 plus 6, 20, 20 plus 44, 64, 64 plus 18, 82, 82 plus 4, 86, 86 plus 114, which is 200. So total head moments is 200. And it is clearly mentioned that power dissipation for 100 cylinders. So power dissipation for 100 cylinders, it has given that for 100 movements, for 100 head movements is equals to 20 milliwatts it has given. But how many total head movements we have? Total cylinders or total head movements, how many we have? 200. So means that power dissipation per 200 cylinders or head movements is equals to 40 milliwatts. So this is, let's consider T1. Okay. Then power dissipation, let's say here I can write power dissipation per head change. Per head change, it is given that 15 milliwatts. 15 milliwatts. But how many head changes we have? 3 head changes. So therefore, 3 head changes are there. That implies, so 3 into 15, which is 45 milliwatts. So 45 milliwatts of power dissipation is there for 3 times of direction, for three times of head direction have changed. So therefore, total power consumption is equals to power consumption is equals to, let's say this is 2 to T1 plus T2 we can say, that is 40 plus 45 megawatts, which is 85 megawatts. So 85 megawatts is the answer for this question. Okay, thank you. This question is from GATE 2018 question paper, and this question belongs to operating system. So coming to the question statement, in a system there are 3 types of resources, E, F and G. 4 processes are also there, which is P0, P1, P2 and P3 execute concurrently. At the outset, the processes have declared their maximum resource requirements using a matrix named max as given below. For example, max of P1 comma F1 is the maximum number of instances of F that P1 is required. Okay, so the number of instances of the number of instances of the resources allocated to the various processes at any given state is given by matrix named allocation. Consider a state of the system with the allocation matrix as shown below, and in which 3 instances of E and 3 instances of F are the only resources available. From the perspective of the deadlock avoidance, which one of the following is true? Option A, the system is in safe state. Option B, the system is not in safe state but would be in safe if 1 more instances of E were available. Option C, the system is not in safe state but would be safe in 1 more if 1 more instances of F were available. And option D, the system is not in safe but would be safe if 1 more instance of G is available. So here this question is related to the deadlocks concept, which is deadlock avoidance. So to solve this question, we are going to use Banker's algorithm. So Banker's algorithm have constructed with majorly 4 data structures, that is allocation, max, available and need. So among these 4 data structures, 2 data structures are available in the system, so in the given statement. So what are the 2? Have a look. So we are having The first data structure is allocation, which is defining the current allocation. So total we are having 3 resources, E, F and G, and total 4 processes we have, P0, P1, P2 and P3. So 101, 112, 103, 200. So this is what the current allocation of P0, P1, P2, P3. Next, maximum. Maximum demand of all these 4 processes with respect to these 3 resource instances. So 431, 214, 133 and 541. So this is what maximum demand of all these processes. Next. So we are going to have the next matrix, which is need matrix. So need is the it is maximum minus allocation, current allocation. So 4 minus 1, 3, 3 minus 3, 3 minus 0, 3, 1 minus 1, 0. Next, 2 minus 1, 1, 1 minus 1, 0, 4 minus 2, 2. Next, 1 minus 1, 0, 3 minus 3, 3 minus 0, 3, 3 minus 3, 0. Next, 5 minus 2, 1, 4 minus 0, 4, 1 minus 0, 1. So this is what the need of each process. Next, available. So according to the question statement, it is clearly mentioned that 3 instances of E and 3 instances of F are the only resources available. So means that the available is 330. So this is what the system we have. On this system we are going to apply Banker's algorithm. Right. So first we are starting with process P0. So what is a P0 need? We are checking with whether as per the Banker's algorithm, we need to check the need of process P0 is less than or equals to available or not. What is the need of process P0? 330 is less than or equals to available, which is 330. So that is true. So means that P0 can be satisfied. So that work equals to work plus allocation. So what is this work is, according to the Banker's algorithm, the initial value of the work is available. So means that you are saving that available into the work. So means that what is available? 330. So means that the work is 330 plus what is the allocation of P0? 101. So since P0 is getting completed, whatever the allocation is there, that allocation should be made available to the rest of process for their completion. So that is what the intention of available plus allocation of P0. So we are making, after P0 completion, we are making the allocation of P0 as available to the rest of processes. Okay, so that is what the intention here. So 3 plus 1, 4, 3 plus 0, 3, 0 plus 1, 3. So 0 plus 1, 1. So this is what the updated available after P0 is completed. So in the safe sequence, I can add P0. Then P1. Need is less than or equals to available. What is the need of P1? 102 is less than or equals to, what is the updated available? 431. So with respect to the G instance, this P1 requires 2 instances, but only one is available. Hence, this particular condition is false. We are unable to satisfy P1 with respect to the G instance, G resource type. It is requiring 2 instances of G resource type, but available is only one instance of G resource type. so that P1 we can't complete. Then we are coming to, so this I can say this execution is cycle 1 execution. Okay, so then we are coming to P2. So P2 need is less than or equals to available. So what is the need of P2? 030. Less than or equals to what is available? 431. It requires 3 instances of resource type F, and those 3 are available. So hence we can say this is true. So then the allocation of P2 must be made available. So that's why we are adding the allocation of P2 to the available. So what is the available? 431 plus what is the allocation of P2? 103. Then it becomes 4 plus 1 5, 3 plus 0 3, 3 plus 1 4, 534. So P2 got completed here. Then we are coming to P3. So P3 need is less than or equals to available. So what is the need of P3? 141. Less than or equals to what is the updated available? 534. So it requires 4 instances of resource type F. What available is 3. So means that P3 can't get satisfied. So then we are coming to cycle number 2. So let's check with the let's check with the P1. So again we can start with the P1. The P1 need is less than or equals to available or not. What is the need of P1? 102 is less than or equals to what is the current available now? 534. So it requires 2 instances of resource type G, which are available is 4, can be satisfied. It requires 1 instance of resource type E and 5 are available which can satisfy. So means that P1 can be completed. So that P1 I can add to the safe sequence. So then work equals to work plus allocation. So what is the work? 534 plus what is the allocation of P1? 112. So then it becomes 5 plus 1 6, 3 plus 1 4, 4 plus 2 6. So then after completion of P0, P1, after completion of P0, P2 and P1, the updated available is 646. With this 646, can we satisfy P3 or not? That we are going to check. Now this is what cycle 2. In cycle 1, we are unable to satisfy this P1 and P3. Now we are coming to cycle 2. So cycle 2, we are able to satisfy P1. Then I am coming to the P3. So P3 need is less than or equals to available. What is the need of P3? What is the need of P3? 141 is less than or equals to what is the available? 646. 646. So it requires 2 instances of resource type F, 4 instances of resource type F. So 4 are available, and it requires 1 instance of E resource type, so that 6 are available which can be satisfied, and it also requires 1 instance of G out of 6 number of available instances of resource type G which can be satisfied. So true. So means that P3 I can add to the safe sequence here. So then work equals to work plus allocation. What is the work? 646 plus what is the allocation of P3? 200. Then it becomes 846. So with this available, we are able to satisfy all the 4 processes. Okay, all the processes needs. So, and at the end we are getting the safe sequence as P0, P2, P1 and P3. This is what one safe sequence. Okay, so the safe sequences are unique as we know that. Okay, so since we are getting the safe sequence, we can say the system is free from deadlock. Free from deadlock. So what is the meaning of free from deadlock is the system is in safe state. So the system is in safe state, which is matching with option A. So the answer for this question is option A.